Okay, welcome back, and let us consider the next part. Okay, so let me consider this. Okay, so this problem again. So let me go back to the beginning of this. So in example 7, we have a solid as in figure 12. Now, the situation is this. If I consider the crosscut, actually, if I consider the cross sections perpendicular to the base, you get a equilateral triangles. And we want to find the volume of this solid. And the base is a circle with radius 1. So the base is the circle with radius 1. And when I consider the crosscut, so the crosscut perpendicular to the base, that means you are considering the cross section here, okay? Then this cross section is the intersection between this plane and this solid will be an equilateral triangle. And the base of this equilateral triangle is defined by this circle. So here's the idea. Given this, the circular base of radius 1, I have a circle with radius 1, so I can assume that the center of this circle is at the origin. Then that will simplify the functions. So given this, the equation of the unit circle, okay, I want to assume that the center of the circle is exactly located at the origin, so that so that the circle of the base is defined by this blue expression. So x squared plus y squared equals to 1. Okay, and for simplicity, let me so at each point x, so when I consider this crosscut, this red triangle has the intersection of this red line with the base. So that red line is defined by this. Okay, so at x, so x coordinate of this point is x, and the these two endpoints are denoted by a and b, and this upper point is will be called b, and of x and y, and a will be denoted by x and negative y. Okay, and since this is an equilateral triangle with, say, length 2y between a and b, since this is an equilateral triangle, the ratio, so between this side, the ratio between height and the base will be square root of root 3y times 2y, right? I mean, because this is an equilateral triangle. So if this is y, then this is a 2y. So this is a right triangle. So the height will can be obtained from the Pythagorean theorem. So y squared plus h squared will be 2y squared. From this, h squared will be 3y squared. So if you take the square root, h will be square root of 3 times y. Okay? So then what is the area of this equilateral triangle? 1/2 times the base the width 2y times height square root of 3y. So eventually you get square root of 3 times y squared will be the area of this triangle. Then what is y in terms of x? Since x and y satisfy this equation, the x squared plus y squared equals 1, y squared will be 1 minus x squared, and so this 1 minus x squared can be plugged in to get square root of 3 times 1 minus x squared will be the area of this right triangle, equilateral triangle. So that is the cross-sectional area. So cross-sectional area is square root of 3 times 1 minus x squared. So if you integrate this from negative 1 to 1, or if you integrate this function from negative 1 to 1, you get the volume. Now, so you can integrate this directly from negative 1 to 1, or since this function, this integrand is even function in x variable, you can integrate this integrand from 0 to 1, and then you can multiply 2 to get the volume. The other part is simple. So in this way, we can find the volume of the solid given in example 7. So problem like this may be given, okay? But example 7 is very difficult because in example 7, no functions are given. You need to find the functions yourself. Okay? So from the information that we have a solid with circular base of radius 1. Okay, then there are many ways to define a unit circle of radius 1. Say x minus a squared plus y minus b squared equals to 1. That will be the equation representing the unit circle centered at the point A and B. But since this the exact location of the point does not change the volume, we have the freedom to choose the center of this circle. So we just assume that A and B are zeros. In other words, we want to put the center of the circle exactly at the origin. Then the equation becomes that in B, so that you have this x squared plus y squared equals to 1. Okay, so I want to have the unit circle centered at the origin. From this, okay, given point x, you need to consider this intersection, which is this red vertical line at x, and you need to find the y coordinate, the value of y, because the value of y will give you the area of the cross-sectional area, right? Now, since this equation of the unit circle is given by x squared plus y squared equals to 1, if I combine that information with this, so if I combine these two, you get the cross-sectional area. The other part is simple then. The remaining part is simple because you can just integrate that simple function from negative 1 to 1. Or using the fact that this integrand is an even function, you can integrate the integrand from 0 to 1, and then you can double the value. Okay. So let me go back to the beginning of the section. So what did we study in section 2? We considered the volume. Okay. If and the idea of this section is one way to measure the volume. So in section 6.2 says the volume can be obtained if you know the cross-sectional area. If you integrate cross-sectional area, then you get the volume. That's the main idea of this section. So your task is to find the cross-sectional area. And as a special case, if I consider the revolution of two functions, so given two functions, say y equals to f of x and y equals to g of x, and then if I consider the interval from a to b, then it will define certain reason. And if this is revolved about a line, say x-axis, then as I said, the graph which is farther from the axis of revolution will define the outer radius. So f of x squared times pi will define the outer circle, the area of the outer circle, okay, and minus the inner radius, pi times gx squared. If you integrate this from a to b dx, then that will give you the volume of the solid obtained by revolution of about the x-axis. Of course, you may consider the revolution in about y-axis. Okay, then the outer radius is obtained by measuring the distance from the axis of revolution and one of these two functions in y. And whatever is farther, that will define the outer radius, and the remaining one will define the inner radius. So if you consider such revolution of curves, the problem is a little bit simple in some sense. But as we observed in example 7, sometimes we need to find the equation ourselves. Okay? In that case, the problem is a little bit difficult. It is challenging. And you need to practice. So in example 7, we need to find the equations. And this is difficult. And that requires some practice. Now, in section 3, we will consider a slightly different approach. It is a similar, but slightly different. So previously, when I consider in section 2, when I consider the crosscut, I mean the cross-sectional area was integrated to get the volume. Okay, so in that case, it is like when you measure the volume of say bread or loaf of bread or some say potato. How do you measure the volume? I mean, if you can cut this potato or bread into slices, you measure the volume of each slice and then you add them. That was the basic idea of section 2. Okay. Now, in section 3, when I want to consider something called the spherical shells. So what is it? So let us consider the problem of finding the volume of the solid obtained by rotating about the y-axis the region bounded by y equals 2x squared minus x cubed and y equals to 0. Okay, so the statement seems to be quite similar to that in section 2. We have the revolution of two curves. But please remember, in section 2, y equals to f of x and y equals to g of x. These two functions are revolved about the x-axis, or x equals to f of y and x equals to gy is revolved about, say, y-axis, right? So what is x? The equation of the x-axis, that is y equals to 0. So the given two functions, the functions of f of x and gx, those two functions in x, those two functions in x are revolved about y equals to 0, or say y equals to 1, y equals 2, and so on. Okay? Or when you have two functions in y, those are revolved about x equals to 0 or x equals to negative 1 and so on. Okay? So those are what we considered in section 2. Okay? So if you have some functions in y, I revolved about some line, say x equals to 0 or x equals to negative 1 and so on. Okay? Now, in this section, I have a function in x. Okay? That is revolved about y-axis, x equals to 0 line. So here in section 6.3, y equals to f of x and another function, say g of x, are revolved about not x-axis, y-axis. So these are paired with y-axis. So x equals to 0 line or x equals to negative 1. So such revolution is considered in section 6.3. So that's the difference between 6.2 and 6.3. Okay? So here I have a function 2x squared minus x cubed. Some function in x is revolved, not about x-axis. Previously, if I have such function in x, we considered the revolution about x-axis. But now I'm revolving this about y-axis. Okay? Then, 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 okay, then when I consider the crosscut, perpendicular to the y-axis, then probably, okay, this curve, this blue curve, will generate some large circle, and this red curve will generate this inner circle. So if I can find the outer radius and inner radius, then the problem will be solved, right? Then, okay, then what is outer radius and what is inner radius? Outer radius or the inner radius is the distance between the axis of revolution and this red curve. So this distance will define the inner radius. What is this then? Well, I need to estimate the x coordinate of this point. What is that? What is it? All I have is the information about this function, y equals to 2x squared minus x cubed. So given y value, I must have the corresponding x values. Okay, so given y, you need to find the two x values. One will define the inner radius and the other will define the outer radius. But the problem is there is no way to find x value from this equation. Okay, so in some situation, it might be simple to find the outer radius or inner radius. So in that case, okay, then the problem can be simple. But in this situation, when y equals to 2x squared minus x cubed function is given, it is difficult to find x in terms of y. So finding x in terms of y is not that simple. So the previous approach is not applicable in this situation. For this function, we cannot use that idea. So we need to consider a different approach. Okay. So we want to consider something called the method of cylindrical shells. Let us consider the figure 2. So figure 2 shows a cylindrical shell with inner radius of R1 and outer radius of R2, and the height is h. And suppose that the difference between the inner radius and outer radius is delta r. So delta r denotes the difference between the outer radius and inner radius. Okay, and for simplicity, let me define r to be the average between the inner radius and outer radius. So r is the average of these two radii, and delta r is the difference between these two radii, and h is the height of this cylindrical shell. And given this, I want to find the volume of this shell. So the volume of this shell is obtained by subtracting the volume of the inner cylinder from the volume of the outer cylinder. The outer cylinder is a cylinder defined by R2, and the inner cylinder is defined by R1. So, and we already know the volume of a cylindrical cylinder. I mean, the circular cylinder. we already considered that volume in the previous section. So V2 is defined by outer radius R2. So the volume will be pi r squared times h. In case of a V1, that corresponds to inner radius. So pi r1 squared times h will be the volume of V1. So this difference, using the fact that pi h are a common, we can write down the difference by this, and r2 squared minus r1 squared can be factored into a product of r2 plus r1 times r2 minus r1. And r2 plus r1 can be written by 2 times this expression, then r2 plus r1 divided by 2. That was what I meant by r. R was the average between r1 and r2. And moments ago, I used delta r to denote r2 minus r1. So, so the volume of such shell can be written by 2 pi r h times delta r. Okay, so 2 pi r h times delta r. Okay, now, so let me review this one more time. So if I have this cylindrical shell with inner radius of r1, outer radius of r2, then I define delta r by the difference, and r is the average of these two, then and height is h, then such a cylinder has the volume of 2 pi r h times the delta r. Please remember this. Okay, now let us consider a solid S obtained by rotating about x-axis the region bounded by this function. So the graph of y equals f of x and two vertical lines, x equals to a and x equals to b, and x-axis, which is y equals to 0. So in other words, if I consider the revolution of the region in blue in figure 3 on the left one, then you get a solid as in figure 3 on the right. Okay, and I want to measure the volume of this solid. So previously I considered the crosscut. Now instead of considering the crosscut, I want to consider a different approach. Okay, so if that the one on the right is this solid obtained by this, okay, then here is the idea. I want to divide the interval into many pieces. Okay, and if I consider this strip, the red one, the red strip, it will generate certain portion of this of the solid, right? And then I want to consider the revolution of next strip, then it will generate something, right? And then I will consider the revolution of the next strip, and so on. So if I consider the revolution of the red one, what do I get? You get the red one will generate some solid will be obtained, right? And if I consider the revolution of the blue strip, it will surround the solid, the red solid. Okay, you will get the blue solid just outside of this red one. If I consider the revolution of the purple strip, you get the outside of this, and so on. Okay, do you understand what I'm saying? So I I I split. So instead of, so when I consider the graph of y equals to f of x and x-axis and x equals to a and x equals to b, instead of considering the revolution of the region in blue as a single piece, I want to consider the revolution of small strip in red, and then the revolution in blue, then revolution in purple, and so on. So if you do this, okay, if you do this, then you will generate many solids, right? And if you add these many solids, you get the solid of the original problem, right? So the idea was, so previously we considered the crosscut, okay, using some knife I considered horizontally or vertically. But now in this section, okay, instead of considering the revolution as a single piece, I want to split the region into many strips. And then let me revolve this, each strip about y-axis. Then you get some cylindrical shell. And moments ago, we learned how to measure the volume of a cylindrical shell, right? So please remember that if I have a cylindrical, so that cylindrical shell can be considered as this is the solid when I consider the revolution of this single strip. Okay, so if I revolve this strip about the y-axis, you get this cylindrical shell, right? So So, so Formula One tells you how to measure the volume of a cylindrical shell. Now, for the volume of a solid in Figure 3, I want to approximate that volume of a solid as the sum of the cylindrical shell, sum of the volumes of the cylindrical shells, which are obtained by revolving many strips. Okay? So the idea is the same. Okay, so I want to consider the revolution of a single strip. Here you see this red strip. Okay, so given this curve, the graph of y equals f of x, between the interval, in the interval between a and b, you generate many points as we did before. Okay, and on each interval, okay, on each interval between xi minus 1 and xi, you choose any point and say xi bar, and at that point we evaluate the function to get the height. Okay, then you define this strip. Rectangular strip is defined, and then we consider its revolution. Okay, then you will get this cylindrical shell. Okay, then what will be the volume of this blue shell? What did I tell you? 2 pi r h delta r. Okay, what is r? The average of these two radii. H is the height, and delta r denotes the difference between r1 and r2. So here, the volume of this cylindrical shell will be 2 pi r h and delta r here. R is the radius, the average between two radii. So there is xi plus xi minus 1 divided by 2. H is f xi star xi bar. And delta r is, in this notation, we usually use the delta x to denote xi minus 1. So delta x is multiplied. So that will be the volume of this single cylindrical shell. And on each interval, you obtain one cylindrical shell. So if you split the interval from between A and B into, say, n pieces, then you get, oops, I'm sorry, the since we used xi bar, so okay, so this is the vi, and see, if I split the interval between A and B into n bins, then you obtain n such cylindrical shells. And if you add them, that will be an approximation of the volume of a solid. And then if you increase the number of bins, number of the small intervals, then the difference between the sum of the volumes of the cylindrical shells and the actual volume will be eventually negligible. So then what does that mean in mathematics? So I have the sum of the volumes of the cylindrical shells, that is this, and that is an approximation of the actual volume of the solid. Now if I let n go to infinity, in other words, if I introduce more and more intervals so that you get more and more cylindrical shells, then you are considering this a limit, and if the limit exists, then that is actually representing the limit of the Riemann sum, and that can be replaced by this integral. Okay? So in section 2, if I know the cross-sectional area, when I integrate that cross-sectional area, you get the volume. Okay? In section 3, this expression is not representing the cross-sectional area. Okay, what does that mean? At each point x, you are considering the so I have so at each point between A and B, I'm considering a very tiny strip, and if that strip is revolved about y-axis, you get a very thin cylindrical shell is obtained, and that volume of this cylindrical shell is approximated by this expression, not the cross-sectional area. Then you integrate this volume from A to B, you get the volume of the actual solid. Okay. So here, that is okay. That is the integrand. You need to okay. That is the integrand, and if you integrate it from A to B, that will give you the volume. Okay, and this method is called the method of cylindrical shells. So when I look at figure 4, I usually think of an onion. When you measure the volume of an onion, okay, when you open any onion, it consists of many shells, right? So when you measure the volume of such solid, such a shape solid, you measure the volume of each shell, and then you add them. Okay, so that's the difference between the approach in section 2 and section 3. So please remember that here the graph y equals f of x graph, okay, the region under the graph of y equals f of x, that means the region between the graph of f of x and x-axis. In other words, y equals 0. And two vertical lines, x equals to a and x equals to b. Okay, these four curves define some region. Okay, and in section 3, when this region is revolved about some y-axis, x equals to 0 line. Okay, in that case, this is one way to get the volume. Okay. If this region were revolved about the x-axis, then probably you will consider, okay? So in that case, you get this. But note, if the region is revolved about the x-axis, then the volume will be the integration of the outer radius which is f of x squared times pi minus the inner radius squared, but inner radius is 0 in this case, and x goes from A to B. So that will be the volume of the solid. Okay, so when you consider the same region here, okay, the region in blue, if that region is the revolved about the x-axis, then probably you will use the formula we learned in section 2. Okay, but if that region is revolved about the y-axis, then probably the method of cylindrical shells will be easier, and you need to integrate 2 pi x f of x. Okay, so depending on the axis of revolution, the volume is defined in different way. Okay, and if you want, okay, if you want, you can read this slide number 8, to get some idea of formula. So some people might prefer such reasoning, but I personally don't like it. So please read this, okay? And if you feel comfortable with this reasoning, you may use this idea. But since personally it seems a little bit confusing, I don't want to explain myself. Okay. So let us consider one example. So here is the function we considered in the beginning of the section. So suppose that we consider certain region bounded by these two curves, y equals 2x squared minus x cubed, and y equals 0, so that we have this red curve and x-axis. Then they have two intersections, and they will define some region. Excuse me. And then, as I said, if you revolve this region about the x-axis, then probably you will show revolution about the x-axis. If this were considered, then the volume will be 2x squared minus x cubed squared times pi dx, and you integrate this from 0 to 2. So that will be the volume. But in this problem, we are considering the revolution about the y-axis, not x. Okay, so in that case, we need to apply a different formula. 2 pi x fx is integrated from 0 to 2. So the integrand is different. So depending on the problem, you need to apply different formula. Actually, once the integrand is given, since this integrand is a polynomial in x, we can easily calculate. So this portion is simple, relatively simple, but the challenging part is to derivation of the integrand. Okay. So please read carefully and check the difference between the approach in section 2 and the approach in section 3. Okay? Anyway, that's the end of today's class, and please be prepared. We have the exam on Wednesday. You have to come to the classroom directly in person. Okay? There is no online exam. You must come to the classroom. I told you. Okay? Please, okay, see you on Wednesday. Thank you for listening, and see you on Wednesday.